Welcome to this lecture on adrenal gland histology and function. Today, we're going to explore one of the most fascinating and critical organs in the human body. We will dive deep into its microscopic architecture and discover how these tiny cellular layers keep you alive during stress. By the end of this session, you will not only understand its anatomy, but also the mathematics behind hormone secretion. To begin our journey, imagine you are holding a peanut butter cup candy. It has a distinct outer chocolate shell and a completely different, soft peanut butter center. The adrenal glands, which sit like tiny triangular hats on top of your kidneys, are built exactly like this candy. The outer shell is called the adrenal cortex, and the inner center is the adrenal medulla. Even though they are packaged together, these two regions are actually completely different organs. They are made of different cells, respond to different signals, and produce entirely different chemical messengers to manage everything from a sudden tiger attack to long-term fasting. Now that we understand the overall structure, let us zoom in on that outer shell, the adrenal cortex. Histologically, the entire gland is protected by a tough connective tissue capsule. Immediately beneath this capsule lies the cortex, which is massive, making up about 80 to 90% of the gland's total volume. Embryologically, this tissue is derived from the mesoderm. When we look closer under a microscope, we see that the cortex is not just one uniform mass of cells. It is actually subdivided into three highly distinct microscopic zones, each with a very specific and life-saving job to do. Building on those three zones we just identified, let us learn how to remember them. From the outside in, we have the outermost zona glomerulosa, the middle zona fasciculata, and the innermost zona reticularis. In medical science, we use a very helpful mnemonic to remember this exact order, GFR. And to remember what each specific layer produces, we use the phrase salt, sugar, sex. The glomerulosa controls salt balance, the fasciculata manages sugar metabolism through cortisol, and the reticularis produces sex hormones called androgens. Each layer is a specialized factory. Moving past the three layers of the cortex, we finally reach the deep inner center of our peanut butter cup, the adrenal medulla. Unlike the cortex, the medulla is derived from neural crest cells. You can think of it essentially as a modified sympathetic ganglion. But instead of having long nerve fibers that reach out to target organs, the medulla works differently. Its specialized chromaffin cells dump their neurotransmitters, like adrenaline, directly into the bloodstream. This rapid release is exactly what triggers your immediate fight or flight response during a sudden emergency. Understanding this microscopic anatomy is not just academic. It is absolutely critical for diagnosing disease. If the zona glomerulosa fails, your body cannot retain sodium, leading to a fatal drop in blood pressure. If the zona fasciculata is destroyed, a condition known as Addison's disease, you lose the ability to produce cortisol and cannot mobilize glucose during illness. Conversely, if a microscopic tumor grows in that same middle layer, it pumps out massive amounts of cortisol. This causes Cushing syndrome, resulting in severe weight gain, fragile skin, and diabetes. The microscopic health of these cells dictates the health of the entire patient. To truly understand how these diseases impact the body, we must look at how hormone production is measured mathematically. The cells in the zona fasciculata secrete cortisol at a very specific rate to maintain balance. We model this using the cortisol secretion rate formula. In this equation, CSR is the total amount of cortisol produced per day. MCR is the metabolic clearance rate, which is the volume of blood plasma completely cleared of cortisol per day by the liver and kidneys. Finally, C is the average plasma concentration of cortisol in the blood. If the gland secretes more hormone, the CSR increases, which forces the blood concentration C to rise if clearance remains constant. Now that we have our formula, let us see this with a concrete example. We have a healthy university student with a perfectly functioning adrenal cortex. Laboratory tests show her average plasma cortisol concentration is 0.15 milligrams per liter. Her liver and kidneys clear cortisol at a normal rate of 120 liters per day. We need to calculate her daily cortisol secretion rate. We choose our standard formula and substitute the given values, multiplying 120 by 0.15. The liters cancel out, leaving us with 18 milligrams per day. This physically means her zona fasciculata cells are manufacturing exactly 18 milligrams of cortisol daily to maintain her normal metabolism. So we've successfully used the formula to find the secretion rate. But what happens when we already know the secretion rate from a hyperactive tumor and we need to predict the blood test results? We must rearrange our equation to solve for the plasma concentration. This chunk of the derivation sets up that exact algebraic rearrangement. We start with our original equation, CSR equals MCR times C. To isolate the concentration variable, we must divide both sides of the equation by the metabolic clearance rate. This mathematical step is the foundation for predicting how a massive increase in cellular secretion will drive up hormone levels in the blood. Continuing from our previous step, we now finalize the algebraic rearrangement. By dividing both sides by the clearance rate, the MCR terms on the right side perfectly cancel each other out. This leaves the concentration variable completely isolated. We then simply flip the equation for standard readability, giving us our final result. C equals CSR divided by MCR. The intuition here is powerful. It mathematically proves that the concentration of hormones circulating in your cardiovascular system is directly proportional to how much the gland secretes and inversely proportional to how fast your body can clear it away. We are now ready to apply this to a clinical scenario. Now that we have derived this new formula, let us apply it to a patient suffering from Cushing syndrome due to microscopic adrenal hyperplasia. His zona fasciculata is overgrown, causing his secretion rate to skyrocket to 60 milligrams per day. His clearance rate remains normal at 120 liters per day. We need to find his new plasma concentration. We use our rearranged formula and divide the abnormally high secretion rate of 60 by the normal clearance rate of 120. This yields a final answer of 0.50 milligrams per liter. Physically, this means his blood has more than 3 times the normal concentration of cortisol, directly explaining his severe symptoms, like rapid weight gain. Having calculated the severe impact of an overgrown cortex, let us visually review exactly where this happens. On screen is a detailed cross-section of the adrenal gland. Starting at the top, you see the protective capsule. Just below it is the zona glomerulosa, characterized by circular clusters of cells that produce aldosterone for salt balance. Moving deeper, we see the thickest layer, the zona fasciculata, arranged in long, straight columns. This is the exact layer that overproduces cortisol in Cushing syndrome. Below that is the branching network of the zona reticularis, producing androgens. Finally, at the very bottom, we reach the adrenal medulla, packed with blood vessels ready to receive adrenaline. This diagram perfectly illustrates the layered factory of stress response. We have covered a tremendous amount of ground today, so let us reinforce the most important ideas. First, remember that the adrenal gland is a remarkable dual organ system, neatly packaged above the kidneys. Second, the outer cortex is divided into 3 distinct microscopic zones that produce essential steroid hormones for salt, sugar, and sex balance. Third, the inner medulla acts as a rapid response neural tissue for emergencies. Finally, we saw how microscopic architecture connects to mathematics, allowing us to predict blood hormone levels based on cellular secretion. You now have a complete foundational understanding of adrenal histology and function. Excellent work.